All right, in this video, we're going to be covering section 5.4 and 5.5. 5.5, I'm just going to be talking through just slightly, but then I will expect you to sort of work through 5.5 by reading it and running the R code and trying to see what the R code is doing and how it corresponds to what the textbook says it's doing. So why don't you pause, copy this panel down, and then press play. Okay, so in section 5.4, we're looking at two samples in bootstrapping, and there's going to be two scenarios with this. The first scenario with two samples is I have two separate populations and I somehow wish to compare them. The second scenario is where I have one population, but it has paired data. So like the 12 divers, they have the semifinal score data and the final score data, and those items were paired with each other, okay? So here, we're going to look at two separate populations and how we can use bootstrapping to compare them in some way, okay? So the scenario here is we're given two independent samples, one of size M from population 1 and another of size N from population 2. And what we're going to do is we're going to bootstrap basically each sample. So step 1 is going to be to do a resample of size M with replacement from the first sample of size M. And then separately, make a resample of size N with replacement from the second sample, okay? And then compute some statistic that compares these two resamples. So perhaps the average of the first resample, minus the average of the second resample, right? Record it. Then repeat this step 10 to the 4th or 10 to the 5th times, recording that statistic each time. And now you've got 10 to the 4th or 10 to the 5th values of the statistic. Let's construct that bootstrap distribution and look at whatever we need to look at, the spread, the bias, the shape, the confidence interval, what have you, okay? All right, so we'll do this via an example. And this is example 5.4 from your textbook. And the R file is a little bit wonky, but it works. And we'll talk about that as we get to it. But here's the setup. We're looking at a question of, there's a hypothesis that males who know they're being observed by a female will have a higher testosterone level than males who are being observed by another male. Okay, that's a hypothesis from some social scientists. So what we're going to do is we're going to measure testosterone levels of two populations. Now, here are the two populations. First population is a bunch of male skateboarders who are being observed by a female, okay? And we'll say that their mean testosterone level is denoted mu sub W for the entire population of these. The second population is male skateboarders who are being observed by a male. Their population mean testosterone level would be mu sub M, all right? And we'd like to ask a question, are the testosterone levels the same? Or is the testosterone levels of the male skateboarders being observed by a woman larger than the mean testosterone levels of the male skateboarders being observed by a male, okay? So we are going to grab a sample from each of these two populations and bootstrap it. So now I'm going to switch over to R, and we'll see how that goes. And I'll put some values in on the board as we get them. Okay. Now, I got my resample data clicked off, and I am here on line 92, upper left. I'm here on line 92 of the folder, okay? Now, you're going to get a lot of errors, and I don't quite know why, because honestly, I don't know why that well, but we're going to get a lot of errors. And I can't show you the data file because when I say view skateboard, it doesn't give it to me. Don't know why, but it's there and this code does work. So on line 98, I'm going to create my two samples, or my first sample. First sample is the testosterone levels of those being observed by a female, so test F. So I'm going to take a subset of the skateboard file. I'm selecting the testosterone column, but I'm only selecting testosterone values that correspond to the experimenter being listed as female. So that's going to give me all the testosterone levels of the skateboarders who are being observed by a female, okay? So I'm going to run that line. I'm going to get an error reading. And then I'm going to do testosterone male. So test M. These are the male skateboarders being observed by a male. Okay. All right. Now I need to know how many people are in each of these two samples. So NF will be the length of the testosterone female, and M will be the length of testosterone male. And let's ask R to tell me how many. All right, so there's 15 male skateboarders being observed by a female, and there's 15 male skateboarders being observed by a male. Let's look at the mean of test F and the mean of test M. So the mean level of testosterone in the people being observed by a female is 9.33, and the mean level of testosterone in the sample being observed by a male is 14.53. Okay, and I can look at the average or the observed test statistic here is the test F minus test M, and it looks like I'm getting negative 5.2, right? Right, and I might have my data set backwards. I'm not sure. I was expecting a positive number there, but it doesn't matter, right? We're just looking at the R code and seeing how it goes. All right, so I'm going to run this bootstrap 10 to the 4th times. Create a vector called test name to record all my statistics, and I'm going to run the loop. And here's how it looks. So lines 119 through 124. I'm going to sample from the female observation. So I'm going to sample from test F, N F of them, that's 15, and allowing replacement. Do the same for the test M. And then I'm going to take the mean of sample F minus the mean of sample M. Okay, I'm going to do that 10 to the 4th times. I take a little bit, there it's done. And then I can look at the histogram of this thing. All right, it looks like we have a bunch of negative values. So I think I got my blurb on the board backward. Okay, looks like the men being observed by men have higher testosterone levels than men being observed by women. Okay, and I'm going to put in my observation in blue, the observed value test statistic, and check to see whether this bootstrap distribution looks normal. Ooh, sure does, but there's the line if you just want to see it. There it is. Okay. And then I'm going to look at the mean of test F minus the mean of test M. All right, I don't know why I need to do that. Let's look at the mean of the distribution. Negative 5.17, standard deviation. All right, and here's the bootstrap confidence interval. So negative 7.93 to negative 2.33. Okay, and later on, they for how you can do the permutation test for this thing. So I recommend you work through that while reading your book. So I'm going to go back to the board here. All right, and I think the alternative hypothesis must have been that. But I got a confidence interval here, a bootstrap, and a 95% bootstrap confidence interval. Okay, so we now know how to construct it with 2 samples. So I could say I'm 95% bootstrap confident that the average difference in the testosterone levels between men being observed by women and men being observed by men is between negative 7.93 bar and negative 2.3 bar, whatever the unit of testosterone measurement is. So that looks like it's supporting the alternate hypothesis. Okay, and I could calculate a p-value if I wish to. Right? Okay, so let's move over to the next example. We're going to do another example here. So copy, pause, copy, play. So here we're going to do the matched pair example. So I don't really have 2 separate populations, but I have 2 separate pieces of data that have to stay matched. So I'm going to return to those 12 divers, and each diver, if you recall, has a semifinal score recorded and a final score recorded. And I would like to find a 95% bootstrap confidence interval for the mean difference in scores. So this is going to be the mean of the final score minus the mean of the semifinal score. It's going to be my test statistic. That is going to be my test statistic, I believe. Okay. All right, so the process. We're going to go from having 2 separate scores to having 1 score. So the way I'm going to do that is I'm going to calculate a vector consisting of the final score for each diver minus their corresponding semifinal score. So there I've taken the paired data and created 1 piece of data for that pair. Now I'm down to 1 sample, and I can do the bootstrapping on this 1 sample. Okay, So I went from two paired data down to a single type of data, a one item of data for each of the divers. And then I'm going to bootstrap that just like we did prior to section 5.4. So sections 5.1, 5.2, and 5.3. And we're looking for a 95% confidence interval. All right, so let's figure that out via R. So back to R. All right, so we need to go down past the horizon. It's a good example. And then match parachute. Okay. All right, so I'm going to create line 234, the single piece of item for each of the 12 divers. And what I'm going to do is I'm going to take the diving 2017 file and take the final score vector minus the diving 2017 file, the semifinal vector. Okay, so that's going to create the one piece of information for each of the 12 divers. What's the length? I don't know. Oh, okay. So I put down diff. So now you see all those 12 differences. I can calculate the mean of the diff. It's 11.975. So on average, the final score is about 12 points higher than the semifinal score. And N tells me that there were 12 divers. Okay. All right. Now I'm going to do the bootstrap. I'm going to do 10 to the 5th times because I have such a small sample of 12. I'm going to create a vector to record my means. And then here we go. From line 243 to 247 is the bootstrap. I'm going to sample from those different scores, those 12 different scores. I'm going to sample 12 of them with replacement. And then I'm simply going to take the mean of my new resample and record it. Okay. So, oh no, it could have been. So take that and run it. Might take a little bit because we're doing 10 to the 5th this time. Okay, it's done. Give you a histogram. Looks normal. It's an average. And then I'm going to ask for the quantile, the 95% confidence interval of that vector. And I'm getting negative 6.58. 85% bootstrap confidence interval is negative 6.58 on the 30.89. Okay. Let's go back. All right. So what can we say based on this confidence interval? Well, it contains 0. And that would be when the final score minus the semifinal score's average is 0, when there is no difference. So if I'm looking to avoid calculating a p-score, since 0 is in the 95% confidence interval, I think I'm rejecting the alternate hypothesis that the final scores are different from the semifinal scores, because 95% probability's got 0 being in there. So if I think it's different, then there's, it appears to be statistically unlikely. It doesn't appear that we've met that 5% threshold. So since 0 was in the 95% confidence interval, that's evidence for H accepting the null hypothesis that the average difference between final and semifinal score is 0. Okay, looks like it probably is. All right, last panel. Really quickly, so pause, copy, and I'll turn it through in 10 seconds. Section 5.5 basically does some examples where you take a different kind of statistic and bootstrap it, okay? So pretty much everything I've shown you has been either a mean or a difference of means, sample mean or difference of sample means. And that's what we've been bootstrapping. But we could use other things like trimmed mean or trimmed means, median or difference of medians, ratio of means if we wanted to, or correlation coefficients. We could do a lot of different things. So I would recommend you read carefully through section 5.5 and crank out the R code as you read along, okay? It would be useful to do this when you're looking at your homework.